Okay, so hello everyone. So I will continue with the lectures for MGM course, and today I'm going to discuss a special type of autoregressive models which are used in NLP now these days, and basically it's a class of methods. So I will start with something called recurrent neural networks. So it's a special case of a neural network. In the last class we saw neural network, but this is one of the variants of neural network. So let us see. So it is mostly used for let's say text, but it can also be used for any let's say sequence data. So it could be speech processing, audio, and things like that. So if we focus on the text, so the today's topic is recurrent neural networks, a variant of neural network. So let us focus on text data. So as we know, text data is a sequence of words you can think of. Sequence. So this is a sequence of data, let us say, or I'm not trying to write word because it could be seen as sequence of characters also. So it depends, like how do I see a sentence, how do I tokenize a sentence. So I will come back to that. So what are the issues we may have if we use the issues with text? So first thing could be is that they vary in length. So text vary in length. So for example, I was late, or it could be I was late for work. So text sentences could vary, okay, in length. So that's one of the issues. So text are, as I said, are very much like also other data, sequence data. So basically it could be speech, music, stock prices. So these are all kind of sequence data. So there is a concept of ordering and time in this type of data. So if we use a another one of the other problems could be how I represent the data. So if I represent the data via so-called bag of words, okay. So for example, if I see these words, dog bites man and man bites dog, then if we look at bag of words, then bag of words are the same, but sentences are different. So just a recall of the bag of word. So basically bag of word means that you define a vector that contains all the vocabulary, let us say capital T, all possible vocabulary words you have, and then you identify them as a position in here, and then you scan a sentence, and then let us say binary. If I use a binary bag of word, then if I scan this, so let us say the dog is represented by let us say V4, and V7 represents bite, and V100 represents a man. Okay, so let us say these are fixed positions for these. So so if we have all the vocabulary in the word, we represent like this, then we give them a fixed position, and then if I have to represent each sentence, then in this case dog bites a man would mean that the representation for this sentence would be basically everything is 0, and then V4 is 1, 6, and then V7 is 1, and then V100 is 1, and then 0. So this is for this sentence, the bag of what is this. But then even for this sentence, the same vector is used. So this is the problem with having a bag of word representations. Different sentences may have the same representation. Okay. So also with the text we have so basically what we want to say here is that ordering matters in text. So ordering matters. Also ordering may give different emotions. So for example, the dog looked guilty, or we can have the defendant looked guilty. So the first one is more, you can say, amusing. That dog is looking guilty. So it also gives you different feelings for the sentence, okay, depending on whether it's a dog or a defendant and so on. So so our interpretation changes with the ordering, with the nouns that we use and so on. Okay. So and word order essentially controls also the emotions, like in this example here. So so languages as such are very difficult. From this what we see is that ordering matters, sequence matters, so what noun and all this are used also matters, what is the context that matters. So hence we need a model which is a sequence type model, which takes this sequence ordering as a part of the assumptions, and that's where recurrent neural network is useful. So if we look into what we have learned from the last class, the typical neural network, and as we saw, typical neural network does not enforce any sort of ordering. So if we give these sentences like this as a whole, then it may kind of the words like dog or the, all this are kind of seen independently, okay, without having any relationship, if I just pass all this as an input in the typical neural network. Okay, so so that's not going to work. So we are looking for a way where some sort of ordering could be introduced. So hence we need a new architecture, and this is why we are studying recurrent neural network. So the recurrent neural network architecture is a simple one. So if the key idea here is to have a new neural network architecture. So let us say my input is X, and then we have Y hat as an output. So this network, what it means is that we have some sort of recurrence going in, that's indicated by this arrow that comes back. So basically the output of this block will be fed in as the new sequences come in. Okay, so I will explain this in more detail. So we have something called recurrent connection. So in this case we have that the hidden layer receives. So what we recall from the last class is that in a neural network we have the layers. So these are this is some form of a neural network here, and this is an input and this is an output layer. So those are inside, we call it hidden. So these are hidden layers, and then we can also call it as a whole as a hidden state. Okay, so the hidden layer receives two inputs. So what is the first input is the current input X, and then it also receives output from the hidden layer from the previous time step. So output from the hidden layer of previous time step. Okay, so here by output of the previous time step is denoted by this recurrent. Okay, so next time I have to draw this again. The next time it will take in another x, and then output of this will be used. So I will unroll this network, and then you will see this more clearly. So in our example, for our example, what it will receive is that first it will receive current text, which is so let us say it receives the second word, which is dog, and let us say the first word that went in was the. So the went in, and then some hidden output was created. So and then output from the previous time step from previous time step, previous hidden layer time step for the input the. Okay, so basically, if I now write this in a more little bit of unrolled way, so that's no confusion. So first it received the, okay, some vector representation of this, it went in, and then some output was created, but then the output from the hidden layers is also, or we also call it hidden state, is fed in, and then the next time dog word is entered, and then output from the hidden time step. So let us say this is h1 and this is h2. Okay, and so this is taken the second one word in the sentence at second time step, and then h1, the hidden representation of the input from the previous time step, is also used in the second step. Okay, so that's what this means. Okay, and that is why it's called a recurrent, because output from the previous calculation is now fed as an input in the second time step. Okay, so so to show this recurrent concept, you can introduce a time variable, and that index will help us show the way on which time we are. Okay, so in this, if I can use the notation ht, and it and then it has xt, and then the output is y hat t, and ht minus 1 is fed in to the current time step. So this is a compact way to represent a neural network. At time step t, the word current word is fed, and hidden state representation ht is created from this input xt and ht minus 1 from the previous time step, and combined with this an output is created, which is y hat t. Okay, so we can unroll this now. So we know that there is a recurrence going on here. So what we can do as a next step is that unroll this, meaning that we write this for each time. Okay, so that will make it a little bit clearer. So let us use this. So we can look at unrolled RNN. So basically we will do this for each time step. So I may have to draw this. So let us say I draw it a little bit below. So I have 4 words, so I will make it for 4 time steps, and then the input that goes in is x at t equals to 1, input that goes in x at t equals to 2, input at x at t equals to 3, and input x at t equals to 4. And the sentence we are looking at is the dog looked guilty. Okay, so the first sentence is the dog looked guilty, and the output that we get is y hat at t equals to 1, y hat at t equals to 2, y hat at t equals to 3, and y hat at t equals to 4. So these are the outputs we get, and since it's a recurrent, so we have this hidden state at h t equals to 1 being fed at hidden state at t equals to 2 and hidden state at t equals to 3. This is being fed, and this is how the recurrent neural network works. This itself is some form of a neural network. These are all neural network or multi-layer perceptron. Okay, so they are like this, and we have seen neural networks can be represented like a graph like this. Okay, so each of these are neural network. So we can see that the encoding for the word the goes at time t equals to 1, and then the corresponding output y hat t equals to 1 is generated. At time t equals to 2, the network takes encoding for the dog, and then the hidden layer output from the previous time step, which is h t equals to 1, is fed in. And then, so this we believe is this hidden state carries the encoded information from the previous word the. Okay, that's the feeling. You can see this as kind of a memory that goes in. So what is interesting in the previous sequence is being captured by these vectors. That's what we expect. Okay, so so that's the way like it fits in this whole sequence, and then it also produces the corresponding output and so on. So what is important is that for each of the previous sequences, we have some encoded information, which is ht equal to 1, ht equals to 2, 3, and so on. Okay, so we can make it a little bit more concrete with the notations. Let us say, so we can think of this as one, let us say, perceptron. In the simplest case, we can think of this as some kind of a perceptron, and in that case, it essentially means that there will be a linear combination of this, and then followed by activation to produce this. Okay, so in more concrete terms, so what my ht can be calculated as, so the math behind it will be y hat t is some activation of v times ht, and ht will be calculated as fu xt plus wh t minus 1. So this could be one way to use xt and ht minus 1. So for xt, the weights of the neural network that we are using are, according to that, it's the u, okay, and the weight that is applied to h are these w, okay, and then after this, some activation happens via the function f. So f is a function that, for instance, if we are here, then f is a function that uses u xt, uses this u. Okay, so let us say we focus at xt, which is 2. So it uses u of xt equals to 2. That's the current time step, let us say, plus w times h t minus 1, which in our case is ht equals to 1, and then we apply some function f. It could be some activation function, let us say, and then furthermore, we may want to, depending on what we want to do here, it's a classification, regression, whatever, or multi-class classification, or so depending on that, we will choose a g function which will be applied. So for the moment, we keep that f and g abstract. Okay, depending on the problem, we will see what could be those. So we will apply a g function, and then maybe, let us say in this case, g will give me some sigmoid, and that gives me values between 0 and 1, and maybe it's a probability value or something like that. Okay, so, and based on that probability value, maybe, okay, I can kind of predict the output and so on. Okay, so we will come back to that in detail again. So let us say we get some output like that, and this is how we can do some calculations here. Okay, so what is important to note here is that there is no subscript used for u and w. Okay, although I'm using subscript for xt to say that this x is from the t time, and ht is telling me that this is an h, this is an ht from the previous time. Okay, so yeah, so before I go there, what I said is, so we have u xt and then w ht minus 1. Okay, here, so we have u xt plus w ht minus 1, and then on this we have applied the f, and that gives us ht, and this ht is used here by applying g of v ht to finally give you y hat. Okay, I just wanted to say this for completeness. So this is the full step, initially internally you do uxt wht minus 1 using this and this, apply f, and that gives you ht for the current, and this ht for the current will be used furthermore, but I use this ht also for the moment to produce the output by applying g function again and put one more weight v there. Okay, so now coming back to these expressions. So this is one way. Okay, you may make it more complicated. Okay, so basically what we have done here is linear combination basically, and then activation. But it could have been a deep neural network where there is a linear combination activation, then linear combination activation, then linear combination activation for L layers. So this network, or the way you produce HT, could have been done via more recursive linear combination activation form, but we have not done that for simplicity. But you are allowed to do that. Okay, you are allowed to do any neural network here with arbitrary length and depth. Depending on the problem ahead, you may not want to use very complicated one either. Okay. Now, one of the most important thing, if you compare with the usual neural network, is that here the u vector, the u, w, and v, you will see that there is no subscript. So there is no sub t or t minus 1 there. Okay. So this actually means is that this is a shared parameter network, meaning that for different, if I go to the different sequence, then the u is not changing. I'm not using different set of weights for u. Okay. So you can also recall what I discussed in the lecture on NAD. Okay, neural autoregressive density estimation. So in this also similar ideas were proposed, where they said that parameters will be shared over certain window. Okay, so in this case what we're saying is that our window is time step difference 1, let's say. Then in this the u at the time step t was the same set of u that I had time step t equals to 1, time step t equals to 2, I have the same set of this. So then you will say, what then why should not you change the weight, because at different time the weight should be different, right? That's what you may say. Okay, but we won't do that. To first of all, to keep the model complexity very the memory demand of this network should not be too high. If I maintain a very different set of weights for each of the time steps, obviously it will be way more complicated and so on. But usually in practice you don't need that. Okay, so the idea behind is that these neural networks are quite powerful. So even with this different set of sequences and then the way they follow certain sequence, these weights will capture the context of words at different time step as well. Okay, so that's the idea, and usually it works. Okay, so this is a shared parameter network, meaning that w and u are shared over time steps. So what does it mean, right? So if I'm doing the training of this network, okay, so training, I will not cover training part, because training, like let's say you can use some Python library and you can build a loss function based on this output and then the actual output, let's say, and then you can do a back propagation basically to compute the gradient. And this could be done automatically by the Python libraries. Okay, there is some idea called BPTT, okay, backward propagation in time. So so one can do backprop and essentially to update the weights of the network. So this is a parameterized network, parameterized by the weights u and w. So I can do backprop. Let us say that's a black box. I use it as a library. I can build a loss function and minimize the loss with respect to the weights, and the weights get tuned. So the fact that I'm using same weights at different time, what will happen is that at each time it will look at the error and it will update the weight. It will come here and it will also look at the error at this time step, and it will continue to update the same weight u for previous time. So basically these weights, since they are shared, looking at the loss at the times, they just keep getting updated as you move backward in time. Okay, so this is one of the concrete examples of shared parameter network, and there are other variants as well. So that's why you don't see these subscript on v and u. Okay, they are shared. Okay, so this is our more or less a framework for recurrent neural networks. So what I want to say is in the notes is same sets of weights, same set of weights are used at each time step. Okay, same set of weights. So this is essentially a shared parameter network. Okay, shared parameter network. Okay, so there is no such concept in the usual artificial neural network that we saw, but these are cases of shared parameter network. Okay, so in this case, now again, depending on the problem at hand, we may see what would be the way output will be created. So as you can already see that if I'm going for language translation, then there may not be one-to-one relationship. Okay, so the dog looked guilty if translated in let us say some other language, then it may not even have the same set of word, and sometimes two words combined give you one word of a different language. So one of the difficulties could be is whether you will have one-to-one output and so on. Okay, so here again you have variety depending on what type of task you are going to do. So let us say if we want to have one example where we do have one-to-one, then one possibility could be, let us say I am looking for defining grammatically, let us say what these things mean. For example, the dog is a noun or adjective or a verb. Okay, and so looked is a verb. Okay, and then guilty is a adjective, and so on. So there we can talk about one-to-one relationship. Okay, so in this problem we can say that this is a problem where one-to-one relationship is well defined, and here the corresponds to certain grammar terms, a dog corresponds to certain grammar terms, and so on. Okay, so and depending on that also you will decide what kind of activation function you're going to use. Okay, so if it's about multi-class classification, then obviously I'm going to use a softmax. Okay, so in this case it does seem to be a multi-class classification. So if the dog goes in, then one of the thing is like whether so out of the many possibilities that it could be adjective, it could be a verb, noun. So out of this, let us say 6, 7 of the classes, which of the probability is the highest. Okay, so that's how we can think of using softmax if we have to characterize this this problem. So another so this was one-to-one, but then there could be variations of this. So for instance, we could have a let us say yeah. So before going to something else, let us look into, yeah, I mean just to like wrap up what I said is like it could be many applications with the different variations in the output. So for instance, if I'm doing some kind of sentiment analysis, then I will see whole sentence or a paragraph. I will not produce any output, and then only at the last output I will say that okay, this is the sentiment in this paragraph is that of happiness or sadness. Okay, and these kind of things. So I will see whole of the sequence, and then I want to produce one output. And then similarly, language translations, usually in a language translation you want to see the whole sentence. Okay, and you won't produce these intermediate outputs, and then later on you will produce the outputs once you have seen one full sentence of a language, then you will produce. So there are many variations here. Okay, so sometimes it could be one input and then multiple output. So one may also think of image. So one image goes in, let us say, but then those may not be needed in this because image may not follow the sequence. So there are many variety of applications, but then only for those we have sequence where we will use RNN. But if it's image captioning, then we may not have to use RNN in there. Okay, so if it's a usual classification problem, again we may not have to use RNN again. So anyway, so let us look into a special example where we want to we specifically look into, let's say, a language model. Okay, so if we look into a language as such, then given a sentence, in general there are many possibilities. So let us say I'm looking at next word in the sequence. So let us say I'm looking at this sentence: she spent the day swimming in the. Now here, as you can see, there are many possibilities here. So it could be lake, it could be ocean, it could be beach, it could be yeah, we can keep it So once we write a sentence, then the difficulty is like there are many possibilities as well. Okay, but out of these possibilities, it's not that we will put any random word here. So there will be certain set number of possibilities. Okay, so in some sense we can say that there is a predictability. We can do this prediction and out of some handful of choices. So in general, language models are indeed predictable. The only thing is which one is the best prediction at that time. Okay, and some sequences are obviously more predictable than the other. So it depends on the sequence, right? So some sequences are more predictable than others. So in a language model, we determine the probability of a sequence of words. Okay, so we would like to determine the probability of a sequence of words. Okay, and based on this probability, we will try to estimate which is the most probable word to be predicted. Okay, so this could be again a conditional probability, and essentially what we are dealing with is autoregressive models. So the words that I have seen, based on those words, I will predict what could be the next word. Okay, so in this case, then we can look at let us say the probabilities like this. Swimming, comma, in the, and let us say the probability is 0.6. So it may happen that after I have seen the word she spent the day swimming in the, and then the probability, what is the probability that I will predict lake? Okay, so this could be probability 0.6. Okay, but it may be that the probability of if I replace lake by ocean, it may be that the probability is less. Okay, it depends. For an example, let us say. Okay, so this is how we model in terms of probability, and essentially it's an autoregressive problem again. So predicting next word in a sequence. Okay, this is what we are dealing with. Okay, and RNN is pretty much suitable for those kind of problems. So overall, we want to know maximize the probability of the whole sentence. Okay, so basically probability of W1, let us say, to WT at the time step t will be product of the conditional probabilities for all due to the chain rule. We can write that. Okay, so I can use this to write. So then the joint probability of W1, W2, WT is product of I equal 1 to t probability of Wi minus 1 W1. So this is by chain rule. I can write the joint probability as product of the conditionals. So this is how I can model the problem of predicting next word in a sequence and so on. So these probabilities can be calculated or captured via some loss function, let's say. Okay, so I may change this sentence, and now I reuse this and I use that sentence, let us say, and then for each of these then we have certain probability. So in this case we are looking at an example of a text generation, let us say. So I have certain set of words and then I'm trying to predict the next word. Okay, so we let us say we look into that problem. In this type of problem, basically when training, we know the whole sentence anyway. So we put something and then we see the output, and then we actually know what could have been the correct output, and based on that we can calculate the loss here. We can define the negative log loss here. So this way we can train our RNN for text generation task. Okay, so this I will reuse this to explain what we want to do next. So basically everything remains same. It's just that this words I will change. So what we want to do is that we want to focus on that sentence now. So the first word in that sentence is C swam in. Basically that's not exactly the same sentence, but I'm writing a different sentence. So she swam in the so let us look at the sentence. She swam in the, and then the blank, right? So what could be the next word, let's say. Okay, so if we look into this sentence like that, and this is a text generation problem, so I put some text and then see what could be the possible outcomes for the next word. Okay, so in this case, if you see the first word, then there are so many possibilities, right? Because if you just look at the first word, it could be anything, right? She was going, okay, she was eating, okay, she is reading. So there are so many possibilities here. Okay, so in this case, if you just stop here, then many arbitrary text completion can happen. Okay, but once you narrow down, then things become more and more precise. Okay, so so let us say I put a word C, and then it produces some output, and then it produces some output with some probability, let us say. Okay, so then let us say we call this probability y hat at t equals to 1. Let us say we call it negative log y hat of swam. Okay, so that's so we're looking at the probability of y hat being predicting swam. Okay, and then in the next word we are looking at the probability of minus log y hat in, the prediction of in. Okay, so this way we have an input word, and then we look at with what probability it's going to predict the next word in the sequence. Okay, so so if it, in case if it does not let us say predict, or if it, let us say, it does not give me high probability of, let us say we are dealing with probability values. If we are dealing with probability values, then this represents the probability of picking the swam word as a next. So in case it doesn't, okay, then the fact that you already know that the sentences in your document have necessarily swam, let us say. Okay, there was only one sentence which had C swam. Then you know for sure that the next word should have been the swam. Okay, in that case you will look into the errors. Initially the weights will be arbitrary, so it will not be doing good prediction. But based on this, and if indeed the probability of this is, the loss is high, okay, the probability with which it will pick swam is let us say very low, okay, then this loss will be very high, and in that case then we will try to use a gradient descent method and update the weights of the network. Okay, so in this case we will update from here onward. So this W, this U was not good, let's say. Okay, then it will backprop, it will try to minimize, update the U so that it learns to predict swam. Okay, if in future it sees C again, then, and same thing can apply again. Okay, so if it's if the next word goes in is swam, and then it predicted in place of E, okay, it predicted something else. Okay, so then the probability, the loss will be very high, because I will compare this with what could have been the actual prediction, which was in, and but then it predicted something else, then the loss will be high. So I will then do back propagation, update U, W, and so on. Okay, until here I will go. Okay, so this could be the fact that it's making an error in the second time step. It could be because of some error it could have made in even in the beginning. So that's why it's important to go until and backprop until the beginning. Okay, and by the way, this h t equals to 1, but then for the initial h t equals to 0, you can take it to be a 0 vector. Okay, or in some cases you may provide some additional context, some suitable initialization for h, but in general you may put h t equals to 0 to be 0. Okay, so this is how RNN could be taught to predict next word in the sequence. Okay, so let it predict something, if it's not matching with the with what could have been the actual prediction, because this text you already have in your document, so you know that it didn't do well, then your loss will be high. So you make it update the weights, and this way you do here, you provide in, and then the next word should have been the, but it predicted the probability of some other word very high, then again the loss will be high, and you keep doing this. Okay, so this way of where you know what could have been the prediction and what is being predicted, and this way of training is called a teacher forcing. So you essentially you know exactly the answer, and hence you can force, and you can think of this as a student making some mistake, and then the teacher says no, you are not correct, the correct word should have been so, and so on. So this way of is called teacher forcing, and this teacher forcing is used to train the prediction problems of next word in a sequence and so on. Okay, so and this is essentially the idea behind ChatGPT and GPT-3. They are based on the base idea of next word prediction. Okay, so this is called teacher forcing. Okay, this method of training is called teacher forcing, and this is used also in other networks. So obviously, like this is a basic idea, and it could be used in any network where we have this text prediction problem. So as I said, the text prediction problem is so this is how we will train a network, and then once a network is trained, I may use this for text generation. So let us say I supply a lot of sentences like that, and I let the network update the parameter weights, and it's very good at, let us say I do this for all the text in the internet, all the books, all the internet websites, all the PDF files on archive files, all the codes, Python codes, any document you can do. Okay, basically you can treat them as a sequence, and then if you have trained them very well, then it could be used for text generation, and so you will provide some set of inputs, and then it will start producing the output, because it has learned to produce what are the good set of outputs to predict. Okay, so that's why it could be used as a text generation. Okay, so in this case, if I have to do a text prediction problem, then in the next step, so I may use this board then in that case. So if I have trained the RNN network, then after training the text generation, so you will provide some text. So let us say you will provide first two words, see, swam, okay, as initial words. So then, since you have provided this, so this swam anyway, like by default it's an input, and then it goes in, and then since it has trained on data like this, it knows that once it sees a swam, what could be the next good prediction. So since it has, let us say, trained on this, then the next good prediction is in. So then it has learned, right? So it has learned, so it will produce in with very high probability, and then during text generation you have to feed the previous output as an input. Okay, because you want to produce one word after another. So then in goes in, and since during training it has learned after in the next good word to predict is the. Okay, so then this the then goes in, and this way it can keep producing next set of text. And this is how the basic idea behind text generation, this is how it is. This is done, training is done via teacher forcing, and this is how ChatGPT models usually work. But ChatGPT models use something called transformer network, which are more powerful, and we will see that later. But the basic idea is next word prediction that's being used in the ChatGPT. Okay, so so that's why this training could also be done in a set of questions, and then the next set of words that follow are answers. So that's why in ChatGPT you can ask question, and then it knows that for a question next set of predictions should be answers. Okay, so when this is trained, you can put question, and then it knows, okay, let me predict after a question there is an answer, and it will produce one word after the other as an answer. So this is very powerful model, next word prediction, and as you can see, GPT-3 is very powerful. Okay, so when doing a generative task, it may be the case that you want to generate some interesting text, novel text. So maybe you want not necessarily to memorize, but but maybe you want the model to predict something which is more innovative. Okay, so in other words, let us say if I have trained my model in all these sentences, and it knows very well what is the highest probability. After C it's a swam, and then it's in, and so on. But if I am asking to generate some new text, let us say, then this predicting the very highest one may not be a good idea. Okay, so in that case, during prediction, rather than picking the highest probable, maybe you choose second highest probable. That will give you a little bit of variation, and since the fact that it's the second highest, it will also be very relevant. Okay, assuming that you have a lot of text. So rather than having C swam, okay, C drank could be also very interesting word to follow. Okay, so when you are doing a novel text generation, then may not pick the very highest one, because very highest one may exactly correspond to the trained data. Okay, so in that case, you may want to predict, let's say, the second highest or the third highest. So then there will be some novelty in the text generation. Okay, so that's another way to create variations in the data. Okay, so this is essentially an autoregressive process. So you have x1, x2 producing x3, then x3 producing x4, and so on. Okay, so all this falls in the framework of autoregressive. Of course, it also depends on the type of data you train. So if you're training only on the Shakespeare type data, then the flavor of text that it will produce will be very closely related to the style of Shakespeare. Okay, so training data does determine what could be your current the type of data that you will generate. Okay, so if you train on like all possible data like ChatGPT and so on, then obviously you see a lot of interesting variations in the data that it produces as an answer to your question and so on. Okay, so more data does lead to better novelty, but it may lead to some bias and other issues, security issues and things like that. Okay, so one of the way to check to evaluate a training model, so is via so-called perplexity score, and this is given by square root of t product of I equal 1 to t p lm, and this is in the form of a ratio. So this is product of 1 by p lm wi minus 1 w1. Okay, so as you can see, this is inverse of the probability. So basically lower is better. Okay, so this score could be calculated on the test data and then compared with what you have produced. Okay, so then based on this, you know how your model has trained. So, and it is also normalized by the sequence length t, because it may create inflated values if the sequence length is short or long. So hence we take a square root of t as a form of normalization over the length of the sequence. So as I said, lower the perplexity score, better the training of your model. But if it is very lowest, then it may look very artificial. You know, sometimes if someone says something very perfectly, then it may not look like a real world. Like usually humans have their own flavor, and we may not be very perfect. So if it's very perfect, then also it may look a little bit strange. Okay, so if we look into RNN, then in RNN it is good that it's a sequence model. So basically we look into the sequences, and then based on that, depending on the problem at hand, sequence sentiment analysis, it could be language translation or detecting the words or propositions and things like that. So these are many tasks that one can do, and as I said, the sequence problems, you can also like see these as some other applications of let us say music. Okay, and you have sequence of notes and so on, and then you may predict the next notes in the sequences. So there are many applications. You can do some Google search and see how, let's say, RNN based music generation, let's say. Okay, so it could be used in many ways for audio data as well. So one of the things that we want to understand is that, yeah, it's true that it's a sequence model, and these guys capture what was encoded in the previous time step. But one of the things is like, will it retain these for longer duration, right? If let us say my sequence length is 1000, then is it possible that after the 1000th step or the 99th step, the encoded vector, let us say h t equals to 99, okay? So will it retain a good set of, let us say it's a very long sequence, and let us say the previous h is now h99 and I am at x 1000. So is it that h99 has represented all the previous words, encoded all the previous memory in a good way? Okay, so that could be one issue with RNN with very long sequences, whether we will have an issue. So usually in sentences, sometimes the 99th word may be related to second word or third word. Okay, so will it remember so far? Okay, will it remember so far back the dependencies which are so far long? Okay, so there have been issues with RNN, and there have been some modifications for RNN, and people have thought about something called LSTM, long short-term memory, and that somehow fixes this. Okay, there is also some issue with this, like technically, let us say, if you look into the weights, let us say, because eventually these are propagated via weights, right? So this memory is propagated via weights, and so one of the issues with RNN, let us say we have this network, but the training part involves back propagation, updating of weights, and so on, right? So usually one of the issues that people face is, well, while you are doing the updates backwards, because of the fact that it's a long chain network, the weights sometimes get, the gradients with respect to the weights sometimes get multiplied one after the other, okay? And because although the weights are shared, but then these intermediate outputs, with respect to these outputs, you are calculating the gradient with respect to W of this, calculating with respect to, I mean, V goes here, right? Yes. Yeah. So then calculating weights with respect to the derivative with respect to these guys, okay? So it will get multiplied, okay? So now depending on these gradients, due to chain rule, there will be product of the gradients of this, and if these gradients all are small, let us say less than 1, the product of 1000 of this will be very small, and overall the gradient will be very small, okay? And when you do gradient descent method, you use the gradient, and if the gradient is very small, there will be no update in the weights, okay? So that's a gradient vanishing problem. It may also happen that the gradients are very large for some reason, then let us say thousands of the gradients I need to multiply, and each of them are let us say even 100 or something like that, okay? So that may multiply by 1000 times, and it becomes very large, let's say, okay? So let us say not 100, but let us say 1000 length sequence, if it goes way beyond that, it goes over the floating point accuracy, it goes over in overflow, because computers have limited max number and limited accuracy for the min number to be represented. So theoretically you can say that what is the problem, but if you implement these things in a computer, then very large number will throw an overflow error, okay? And if you're implementing in Python or something, it will throw overflow, or if you're doing operation with this, it will throw a NaN, and so on, okay? So there are issues with RNN, and so hence there was some changes in the RNN architecture, and a new architecture was proposed, which is called LSTM. So just to give you a context, that languages sometimes have long-term dependencies. So for instance, if I look into this sentence, so long range so for instance, this word he was supposed to meet his friends at the show, but something came up at work, so he called them to say that he would be late. So if you see here, then the word them refers to his friends. So there is a relatively long term dependency. So them refers to a very far away word which is friends. So one of the question is, will RNN capture this? So let us say friend occurs at 1, 2, 3, 4, 5, 6, 7th. So H at the let us say 7th place, H7, will it, okay, the word the information captured up to H7, which includes friends, okay, will, and even those words that follow, because they also refer to in some way the context of this word. So even the friend which is related to them, will that be captured in a memory which is our running HT? So will it be well represented so that them can be related to friend, okay, later on. So usually RNNs sometimes with this very long sentences can usually can have difficulties with very long sentences. So so this is one of the things that we expect from RNN. And another things are issues of RNN is, as I explained just now, the concept of exploding gradients. This is during training, obviously. And there is also problem of vanishing gradients, as I said. And this is obviously during training as well. Okay, so exploding a vanishing gradient, it happens when you do the training and then you compute the gradients, and these gradients are products of many of these, and they may vanish due to a lot of multiplications, and then also they may explode also. So these are the problems with this. So some of the simple remedies for this would be, let us say people have tried, let's say, batch normalization, or let us say weight clipping. So let us say in some cases, if the weights are very high, what if I divide by the largest weight, okay, like normalize the weights in some way, okay, or what if the weights that I'm initializing initially are a good one, okay, not let us say the arbitrary weights that's leading me to exploding gradients, maybe something which is very normalized, let us say, to begin with, okay. So these are a few things people have tried, but still the issue remains, and hence we go to something called LSTM, okay. So in LSTM, basically the whole setup remains the same. It's just that what goes inside, it is changed, okay, and the way HT is computed is also changed. So what happens in LSTM is that we define something called cell. So we call it, in the LSTM language, we call it cell. Okay, so this is called LSTM cell. So the way what LSTM works is that so the way LSTM will now work is that it will produce HT which is a better one. Okay, in other words, HT which does not get diminished in some way, okay, due to long chain in the sequence and so on. Okay, so this we call it LSTM, long short-term memory. So now we will discuss this LSTM cell, okay, what exactly it is, and why it can prevent this problem of not retaining the relationship, or the fact that there are weights involved in the memory blocks. Then what could we do so that during training the vanishing or exploding gradient problem that destroys the information that could be somehow retained. Okay, so LSTM comes up with a unique concept of a memory state which does not necessarily have direct weights involved. Okay, so now we will see that next. So what I will do is I will I will use this one itself. So this is where we will focus now. So now we discuss something called LSTM, and this is called long short term memory. So in this we can draw this cell state is the main thing. So here I will draw a big block which is the cell state. Let us say I draw it big so that we can see it more clearly, and then the input of this is the previous ht minus 1, and another input is xt, the sequence in the current time step, and then this goes with a block which represents addition, and then we have something called forget gate, and this is a sigmoid function, and this xt goes in, and this basically this ht minus 1 goes in, and this is xt that goes in. Okay, so this is called a forget gate. This ht minus 1 and xt are added here, and then it goes through the forget gate, and then we have c t minus 1, and then so this is what I was talking about. LSTM has this special cell state variable, and this doesn't involve any weight, direct weights. So that's why maintaining this state is good for retaining the memory for long term. Okay, although ht is there, but what is used as a memory you can think of is the cell state, which does not involve weight. The fact that there is no weight, then while doing gradient descent, this may not get directly affected. Okay, although there will be weights here, but this is untouched. So this is element wise multiply, and this function f is our forget gate. So this is defined to be ft is sigmoid of uf xf plus wf ht minus 1. I mean, yeah, that's fine. Okay, so this is xt, I guess. Excuse me. Yeah, so earlier I said it's plus. Actually it's not plus, it's like they are like combined, like they are taken together, but they are operated like this. Okay, so I take two of them together, collect them, and I may concatenate them and concatenate u and f, and then apply them on concatenated xt and ht minus 1. That's possible. But anyhow, ht minus 1 is there, xt is there, and then I have the corresponding weights for the forget gate, and then the these are both are the weights. Forget uf and wf are the weights for the forget gate. And so one thing to remember is that this is a vector, and sigmoid, the output of the sigmoid, this is also a vector. Okay, so basically sigmoid is applied on usually on scalar, right? So but then in this case sigmoid will be applied on each component of the vector, and output will be a vector as well. Okay, so here indeed it takes a cell state. So this takes a cell state, this call it a cell state. So ct minus 1 is the cell state, and then so this forget gate, as the name suggests, it tries to see which of the information it's supposed to retain and which of these it's supposed to kind of forget. So basically it will create some probability values, and then it acts on the ct minus 1. So this is the memory that we are retaining. So by the effect of applying this with these weights pointwise, if some of the entries are small, then the corresponding entries of ct minus 1 will be forgotten. Okay, and if it is close to 1, then those will be highly retained. Okay, so although this is an architecture, during training the neural network, although we interpret it like this is a forget and then so on, but during training this is our model, and during training we expect that this is how it will correspond to, that it will forget or it will retain. Okay, so this is the first thing, which is forget get, and these weights that correspond to ht minus 1 is wf. So these are the weights wf, and these are the weights uf that goes that correspond to these. Okay, so at this stage the cells know what to retain and what to forget. Okay, that's the meaning of this gate. Then we go to the next set of steps where we call it input gate. So input gate is again is abstract concept where we say what information we need to add from the inputs that we have received and from the memory that we have. Okay, especially from the inputs that we receive, and later we will see what to contribute to the running memory variable here. So then I'm going to rub this, and then I will focus on the input get. So this is the output ft from the forget gate, and this is used here. Okay, and then that's exactly the role of this forget gate. It stops here. It just does its contribution to the cell state, which is the memory state, and then there are other gates which follow, and they will have their own contribution to this running memory variable. So let us focus on the other other states. Forget the gates. Okay, so these guys continue in the next step, and then we have a gate called input gate. So input gate, again it's sigmoid, and then we have this, and we also input this. Okay, this will continue further as well, so I can draw this arrow. So this this ht minus 1 is taken as it is, although it was used here, but it's not affected when it comes here. xt also comes unaffected until here, and then there is an input gate. So the input gate output is, I can denote it as I underscore t, and this is sigmoid of u input xt plus w input ht minus 1. So as you can see, these are the weights of the input gate. These weights are different from the weights of the forget gate. Obviously, forget gate has u underscore f and w sub f. Okay, so this is output. Again, you can see it's a linear combination and sigmoid activation. These are simple operations going on here, and that gives me some vector it. Okay, so this the interpretation of this is that this serves as a mask to determine which new info to add to cell state. Okay, so as you can see, we are building an architecture with an abstract concept that we introduce. Okay, but network, it will be the network which will try to go through these gates and have its interpretation and so on. Okay, but when we are designing, we are thinking that okay, this is a forget gate, and this is how conceptually I want to negate what goes in, and so on. Okay, the idea here with the forget gate is that since it directly affects the cell state, we believe that it's doing a refining of what goes in the memory to retain what is not to be retained. Okay, but the explicit representation learned by the network will be very abstract, because the words that goes in, it gets embedded. The previous context also gets embedded via, these are all vectors, they get linear combination activation. So the inner representations are very, these are embedded representations. So okay, so in other words, if I've seen a set of words, then it's not exactly clear that certain word will be explicitly dropped just because these words don't remain intact as words, because they get embedded as vector. Okay, but somehow the network will learn. Okay, what a network will learn a embedded information of the sentence. Okay, so that's what we mean. Okay, so that's why I say these are abstract concepts. It's not as if the network keeps these words and then says I'm going to delete this word. Okay, it doesn't happen exactly like that, but somewhat close. Okay, yeah. So that's what we try to understand here. So so this is our input gate, basically what is to be added. That's how we interpret this, what is to be added. And then there is a gate called cell update. So based on this input, and then there is another set of another gate, and that we call it a cell update. So then I'm going to rub this and then introduce that cell update. So from here, what we have is what we produced from here is f. The notations I use is ft, and this is what we produced so far is it. Okay, which was sigmoid of uf and so on, and this is also sigmoid of ui and so on. Okay, and then we have a cell update gate. Okay, so let me see if I have the full picture written here. So then we have something called cell update. So this follows tanh. As you can remember, tanh is also some activation function, and so far we use sigmoid, and then we are saying tanh, and it also takes these ht minus 1 and xt. Okay, and we can call this as wc uc. they come unchanged, ht minus 1 and xt, and then they go in, and then this cell update produces this, let us say, something called C tilde, and so let us say the output produced by this is C tilde. Okay, so C tilde, I define it to be like I have done it for other. It is also tan H. So it is not sigmoid now. So it is UC xt plus WC ht minus 1. Okay, so these are the weights of the cell update gate. Okay, so that's how we produce C tilde, and then obviously it has its own set of weights, UC and WC, and then so this represents new. This is how it's interpreted. So new information is available for adding to the cell. Okay, so this is how we interpret it. Like there is this input, what needs to be added, or and then we add something more for maybe, let's say, additional context. They're saying that is there something new information to be added again. So we essentially we're giving more representative power here, and then we change based on this C tilde and IT and also FT. Based on this, we have a we update the new cell state basically. So this cell state, if you can see, it has not got any update so far, but then here it gets pointwise multiplied, and this IT goes in. So IT is being pointwise multiplied with C tilde, and if you remember the CT minus 1, which became CT, and CT was CT minus 1 pointwise FT. So far what we had flowing through this is CT minus 1 FT pointwise multiply. I can also write it like a dot. Okay, so until here this was the case, but then we want to use this now. So we want to do IT pointwise multiply with C tilde. So overall, with this two, the CT that I will get will be CT minus 1 FT plus IT pointwise multiplied with C tilde. So IT pointwise multiplied with C tilde. Okay. So this is how the memory will flow, and this is what I call memory. Okay. And remember that this block has no learnable weights. This is the main idea. Okay. We put this separate. Of course, there are weights here, and they will feed in what is to be forgotten, or what is to be updated, and so on. But this guy, there will be no back propagation because there are no weights involved here. So there will be no back propagation through this cell state. Okay. So this CT then gets continued in the next block in the next time step. Okay, so all this is happening for one time step. HT minus 1 came, XT came, but CT is retained separately. Okay, because earlier we had a problem where we have only HT minus 1, and due to gradients weights, this memory, we were treating HT as a memory initially, but then it can lead to problems. But then we maintain a separate memory channel. We can interpret it like a memory channel, okay, which does not have any weights, and that fixes the issues we have with RNN. So then we have finally we have an so-called output gate. So I will kind of use this, rub this, and just keep C tilde. So then we have finally output gate, and output gate again follows sigmoid, and these continue, and this also takes HT minus 1 XT, and this output we can give a weight W0 and U0, and then it produces the output OT, let us say, and OT is sigmoid of U output XT plus W output HT minus 1. Okay, so this is our output, and this CT continues to the next cell. Okay, So remember that in RNN, we had, what we are doing in RNN is we are just changing the cell block, right? So if you recall, in RNN, we had this. Okay, so we have this ht minus 1 xt, okay, and this we call it cell. This whole block corresponds to the cell. Okay, the only difference now is that there is some kind of a CT going in, and this ht still flows to the next one, and obviously xt is fed at the next time step, and so on. So all in this is fine. This is similar to ht minus 1 xt. So we will see how ht will be processed. But one thing is clear: we have this CT state that is flowing across the cell, and that has no learnable weights. Okay, that's independent. But it is indeed influenced by these gates, obviously. And then so we have this output gate, and this output gate produces this OT. Okay, so once you understand this, I'm going to remove this, that we have this OT now, and so we have this OT, and this OT will affect. So this combined with CT, basically it's pointwise. So here we capture the updated CT, and combined with OT, we do the pointwise multiplication of this, and this we treat it as HT. And this is the HT that I'm talking about. So we are passing out HT. We have the CT that has been calculated. Okay, so these are the two outputs this cell is producing, CT and HT. Okay, and this could be now repeated over a time step, and the same HT also is used to produce the output, right? So this HT is then also used, because this is the hidden state, right? So HT is produced here, and this HT is further used to do some activation of f of HT and so on to produce output YT. So this HT also should go up. So hence from this cell we want to pass one HT up, okay, for output, to use it for the current output YT. Okay, so this is the basic idea behind LSTM, and the main concept to learn is that in the usual RNN we were propagating, we were updating the parameters via this, which weights were associated with this H, which we were treating it as a memory state, but that led to difficulties if the sequences were long. If the weights were not properly updated, those memory HT could be lost or overflow and things like that. And hence with this we kind of maintain essentially a weight-free cell state, and that kind of remedies some of the issues that we have with RNN. Okay, so again you can continue with whatever sequence problem you have. Okay, predicting the nouns, adjective, and so on, or predicting the sentiment, or doing language translation, or doing text generation. Okay, teacher forcing, all those, again, all this happens here. Okay, just that the cell state is removed here, and obviously here there are weights involved. Okay, so there are weights involved are WF, UF, and then here also the weights involved are WT, UT, and then so on. Here you have WC, UC, and so on. Okay, so of course there will be loss function that will be made from here, and then there will be a back propagation, obviously, to update the weights. That's how the networks learn, right? So you are supposed to update the weights of the network based on the loss, but updates happen only here. This, which we represent as a memory, there are no weights, and that helps LSTM. It's a good improvement over RNN. But later we will see there is even a more effective variant, which is more popular, I would say, especially if you want to exploit parallelism and so on. Then there is a network called transformer, which is more popular these days. So we will see that again at some point.